Yeah, thank you.
Yeah. So hi everyone, welcome to Benjamin Christie's Thesis Defense. We're really excited for this. My first defense as a committee chair, so I'm really excited. So Ben joined us. Well, actually, he was an undergraduate here at Virginia Tech in the mechanical engineering program. He took courses with me, with all the professors, I guess, on his committee, with Bernard and with Kabe as well. And he proceeded through the UGG program to continue on to his master's here, where he's a researcher in our lab. And he's actually got two really excellent papers that he's going to talk to you about today. One that's gone through one round of revision is kind of like at that final stage with a journal submission, and the second one we just submitted recently for the IROS, International Conference on Robotics and Operating Systems.
Intelligent robotics and
yeah, something along those lines. So with all that said, Ben's got the Smart Scholarship, and we're excited to see what he does next. I know he's starting up his job this summer. So with that, please take it away.
Thank you, Dr. Losi.
Yeah.
Before we begin, I'm going to admit this straggler. Okay, now we should be good. All right, so today I'm going to be talking to you about my work in adaptive communication interfaces, specifically how it relates to collaboration in HRI. And I'm very excited about this research because it's sort of an unexplored field, specifically the subgroup that I'll be discussing today. Before we begin, discuss the outline for this talk. So I'll have a brief introduction into communication in HRI and the two ways that it's commonly solved for. And then we'll discuss more precisely the problem statement that we're trying to address. And I'll discuss my first paper, which is the limit algorithm learning interfaces to maximize information transfer. And then our second paper, which is the IROS paper that you mentioned, which is more on how do you accelerate the adaptation between the human and the interface. And we can do that by enforcing some user-friendly priors that we find intuitive while still personalizing to the user. And after that, we'll conclude and have an appendix if anyone has any more questions. And I assume after that, we'll do general audience questions and then y'all will be kicked out. So, okay, so, oh, there's audio. I didn't realize that. I should have unmuted. Okay, anyway, so we have many different ways that robots can communicate with humans. And typically, these interfaces are either predefined or loosely predefined in a set way to either communicate how they've learned, but the actual mapping between that information and the human's perception is predefined. Or there are other ways for those mappings to be defined, and those are ones that the interface learns via the human's performance or their known task reward. And we are interested in cases where we can do neither of those things. We can't predefine the interface because there's not a mutually understood method for communication. And we don't know what the human is trying to do, nor do we wish to learn what the human is trying to do. Because you may want to tackle this approach using something like inverse reinforcement learning, where, okay, I don't know what the human is trying to do, but I can observe the behavior. Maybe I can learn what they're trying to do and then send information to them that helps them accomplish that goal. We're not interested in that. We want to define an interface that can be transferred between tasks in a task-agnostic way. And this problem statement clearly illustrates that. We wish to learn a task-agnostic interface without knowing what the human wants to do or how they interpret those signals. We want to provide signals that helps them accomplish their goal, whatever that may be. And before we really dive into this talk, I want to address some common variables that would be discussed in this talk. So I'm sure you've all seen these things before. We have the system state, the human action. Sometimes there might be a robot action in some of these states or some of these environments. Not always. Sometimes there's just an interface communicating with the human. And most importantly, we have hidden information in the environment that the human could not possibly observe, but it's pertinent to their task. So let's say, for example, you're trying to navigate to the position of a phone that you've lost. And you're trying to use like a GPS tracker or some LED interface to navigate to that phone, the position of the phone would be the hidden information and the signals would be the LEDs that you have like on your wrist or something along those lines. And that can be transferred to many different cases. Also, I'd like to mention that we are analyzing continuous spaces in this talk for the most part, but the methods I show in this presentation can be applied to discrete settings as well, but those aren't as interesting. So specifically, the policies that we're going to discuss are the human and the interface policies. We're not interested in any other agents within the environment. for meaning or reasons I'll discuss later. And we assume a deterministic environment. This could probably be extended to a non-deterministic environment, like a stochastic environment transition function, but I am not discussing that in this presentation. In some of the environments, there's an additional agent or a selection of agents that are acting upon the environment state, which is shown by U. In some of the user studies, there's U is 0 for all time steps, but sometimes it's not. And you can see how the interface changes to accommodate the human's interpretation of the robot's actions. And I should also clarify that the interface and the robot are separate here. We have a robotic interface that communicates to the human, but it's completely separate from any other agents that are acting in the environment. Okay. Now, as I discussed earlier, there's actually a closed form way to solve for an optimal interface, assuming that you know how the human interprets the information and you know their task reward. Unfortunately, we don't have access to either. Now, if we had access to one of these, we could learn the other. But since we have access to neither and we can't learn one without the other, there's actually an infinite number of possible combinations that yield the same behavior from the human. Therefore, we can't assume how the human or what the human thinks the hidden information is, because like we can't learn either of these two things. So we actually have to come up with a different approach for this that doesn't account for either of those two variables. And to do that, we'll use some ideas from information theory. And I'm going to give a very brief introduction to information theory. I have some interesting papers in my appendix that you feel free to read. But for this talk, I'm just going to give a very surface level introduction to information theory. In Claude Shannon's ultimate paper, I think it was a mathematical theory of communication, he discussed entropy and mutual information. And these are two very powerful quantities that relate sets between each other. It's essentially the randomness of a set given another set, or the randomness of a random variable giving another random variable. And this idea is very powerful because you can actually have nonlinear patterns between data sets that mutual information and entropy, for that matter, can expose that other coefficients or regressions could not possibly expose. And we can use that to find an optimal mapping that, or at least correlate the human's behavior with some hidden information. Now, these values are scalar, but it's useful to think about entropy and mutual information, which I'll introduce in a second, as spatial quantities, because probabilistically, the more you know about a variable, it's possible that you'll have a lower value of entropy. For example, a uniform distribution or a random variable that's sampled from a uniform distribution has maximum entropy, but a deterministic variable has zero entropy. And, well, I should say a one-to-one mapping or a bijection has zero entropy. So that's true for all one-to-one bijections. And that's not something you can expose with another correlation coefficient. So I feel like that's very, very important to address. And as you can see on the graph on the right, mutual information, which is what we'll discuss more in this talk, is a combination of two entropy terms. Basically, it's the randomness of one variable given another, or the randomness between those two. And this took a lot of thinking. This took several months, but we eventually came up with maybe a way to correlate or maximize the efficiency or measure the efficiency of an interface. And you could do it by analyzing the human's behavior, seeing how noisy they are for a particular hidden information at a particular state. So going back to our example, let's say you're trying to look for your phone and you have no idea what the signals that you're receiving are. Well, you'll navigate around, your actions will be mostly random, and then maybe the position of the hidden phone is revealed to you, and you're like, okay, well, maybe this signal corresponded to a different location in the environment than I expected, and you'll adjust your own mapping. And the interface will also adjust to you to maximize this. So as the human is more noisy, this value will be lower. It'll be like more zero because there's no way you can encode the human's actions or decode the hidden information from the human's actions. But if the human does understand the interface, then they'll be able to infer the hidden information theta, and they'll act according to some optimal action given the reward function. So in that case, this mutual information would be high. Now we can rewrite this mutual information term in terms of the human and interface policies. And it's very messy. This is over continuous spaces. There's integrals everywhere. We don't even have access to the human's policy. So there's no clear way to calculate this directly. Even if we had a model of the human, we couldn't tractably calculate this because we have continuous spaces. So we instead come up with a tractable approximation to this term, which is known as conditional mutual information, CMI. And we do so with 3 neural networks. Now, for those that aren't familiar with neural networks, you can think of it as a mapping from one variable to another that's parameterized by what you see in the subscript. We call them weights. And those weights are updated to minimize something called a loss function. So anytime you see an L in the slides, think of that as a function that you want to minimize. Like if it's 0, then the neural network is doing great, generally. Very, very generally. But just think about that. Referring to Claude Chan's paper, he initially introduced mutual information as a way to measure the amount of information that a variable encodes about another. And we rephrase that metric as decodability, as you'll see in a few slides. So if you refer back to the fraction that was in the operand of the logarithm, you have 11 in the numerator and 12 in the denominator. So approximately maximizing mutual information would correspond with maximizing 11 while minimizing 12. This is a rough approximation, and I would posit that 12 is much more important than 11, as you'll probably see later. So to maximize 11, we introduced this human loss function. Now there's 2 ways of thinking about this loss function. First, note that the weights of the human model are the only weights that are updated in this loss function. The weights of the interface loss function are not updated. We aggregate over many interactions some state, action, signal, data pairs, and we try to update the human model in a way such that the actions that it takes at a particular state and signal match what we observe. Basically, we're just behavior cloning the human model. Now, this does maximize 11 because for a particular state, we want to maximize the amount of the distribution of actions that the human can take. And I should emphasize that pi h is the actual human policy, but we rephrase pi h as the neural network h that you'll see. Now, to minimize 12, we do something a little bit more complicated. We instead roll out a simulated interaction over a set number of time steps, and we try to decode data from that trajectory using that decoder network delta, which could be something as simple as a matrix. It could also be, in our case, a set of linear layer networks with no rectifying units. And it could be more complicated than that. The important thing is the human never observes delta. It's solely used to update the weights of the interface. So you'll notice that the loss function updates the weights of the interface network and the decoder network. And that directly impacts the decodability of the interface during the interaction. And this directly minimizes 12. So just like before, there's 2 ways to think about it. I like to think about it as we're trying to maximize the decodability of the interface's signals, but you can also think that this directly minimizes 12. So together, we approximately maximize CMI by using those 3 loss functions, using a combination of those 2 loss terms. And those 2 parameters are just chosen by the designer. They could be anything. Typically, in our studies, we used 1 and 1. If anyone needs a brief review, here's the pipeline. We have an actual interaction with the human, and then between interactions, or even perhaps online during the interaction, we update the signal interface using the decodability of the human's actions. And that, since we do not have a model of the human, we must learn how the human responds to the signals, which is why that human network is necessary. Okay. So we weren't actually sure if this worked. So we ran some simulations. And we started with some very, very simple humans because if you have a very, we initially tried using like a multi-layer perceptron to model the human, but multi-layer perceptrons are very powerful and they can basically inverse any mapping. So if we use simple humans, we could try to gauge if the interface is providing productive signals, if it's actually updating to the human's behavior. And we tested this in several environments, but they all have the same idea where the human's trying to navigate to a goal position. And the closer it is to the goal position, the better, the higher its reward is. And the human only observes this reward at the end of an interaction. So essentially, the hidden information is revealed to the human at the end of the interaction. We compared this our approach called limit, which is the combination of the two loss terms, to several baselines. Of course, like a naive baseline, which is just a basic matrix multiplying the state and the hidden information. And we also used Gaussian process regression to model the human and the interface using a dynamic matrix. Note that all the signals here are scaled from -1 to 1 using tanh. We also just compared using only the human and only the interface loss functions. And we note that limit performance much better than baselines, even in 1 degree of freedom environments. But what I think is really killer, and you can see in 2 degrees of freedom as well, it outperforms. What I think is very killer is that when there's a dimensional mismatch between the signals and the hidden information, limit still performs very well. And this is surprising. And the fact that it outperforms Bayes is even more surprising because Bayesian optimization has direct access to the image reward function. So the fact that Bayesian optimization doesn't immediately go to 0 is very surprising. And that's mostly due to the fact that the humans update between interactions. And in that regard, Bayesian optimization lags behind the human when it's updating the interface. So there's more fighting between the two in co-adaptation. Instead, by maximizing the decodability of the interface, we can more swiftly co-adapt with the human, even for very simple policies. So to verify that this works on actual people and not just simulated humans, we had a 4-part user study. So first we tested online, see if people could navigate to or select the position of a phone in the 9-grid space, given some 2-dimensional signal. So the signal we see on the right, where do you think the phone position is relative to the human? And the user made their guess, the position of the phone was revealed, and then we moved to the next interaction. And between interactions, the interfaces were not updated. So it defeats the purpose of the loss functions, except that in both of these, for both baselines, the interface was pre-trained with a simulated human so that the signals would be more clear. And we found that limit outperforms online in one time step interactions in 2 degrees of freedom, both subjectively and objectively. And this was a very, very exciting result. So we moved to an in-person user study as well, and this was a 3-part user study. The first of which was a 1 degree of freedom task where the user was provided with some sound. And they moved the arm left and right, depending on what they thought the sound corresponded to in the environment of the position of the robot arm. And I have a demonstration. Hopefully it'll play. You can see here that Bayes and limit perform about the same. Limit's marginally better in terms of error for this individual, but in terms of efficiency or like average distance traveled over the course of an interaction, it doesn't perform as well. And this is sort of to be expected because Bayes has more information than limit. It has access to the human's reward function, which we do not assume access to. And it should outperform in lower dimensional settings. So the fact that limit is close to Bayes in performance in these lower dimensional settings is promising. On the bottom, you can see how close he got for each interaction. With that, we can move to the next part of the user study, which is the 2 degree freedom space. It's very similar, except that the interface is an LED or a set of LED strips. And the user tries to navigate to a position in the environment where they think the lights correspond to. And I reveal the actual hidden information position, and then we repeat. all the while, the interfaces are updating to the human between interactions. And here's a demonstration. As before, limit performs a little bit better than Bayes, not by much. I'm not sure I should admit that person. And and I I thought that limit would actually perform much better than Bayes here, because Bayes seems to explore when the human is varying between interactions. Because you have to remember that this is co-adaptive. The human is adapting to the interface, but also the interface is adapting to the user. So it gets very complicated. The most difficult environment was, oh, I'm on the wrong side. Most difficult environment was the haptics environment. And this is for a variety of issues. First of all, this is 3 degrees of freedom. So in and of itself, it should be more difficult. Second of all, this interface is, it's difficult to interpret. And our interface algorithm does not have access. It doesn't know the fidelity or the resolution of the signals. So it must learn that over repeated interaction. It has no access to that directly. And, oh, I'm sorry. You'll notice that the human struggles with this interface a little bit. Although limit does outperform Bayes here, Bayes begins to struggle in very higher dimensional settings. You'll notice limit's also more efficient. The human's not traveling as much over the course of interaction. And I think we accepted these results. We wanted to push for more, but you'll see what changes we made to accommodate this. The only setting where we had significance in terms of the error was the lights, which sort of makes sense. The interface is much more clear in lights, so the human can actually interpret the signals. But subjectively, oh, I'm sorry. People were more efficient in all tasks, which is good. And you can see that in terms of time as well. And people subjectively preferred interfaces that were optimized using limit, which is good. However, we weren't fully satisfied with these results. So I'll transition to my second paper, which is about accelerating the interface adaptation using user-friendly priors. So we know that humans have biases in their perception. And this has been shown in psychology research and neuroscience research and language research. And we can take advantage of these biases to produce intuitive interfaces. Without knowing how the human will interpret the signal, we can provide interfaces that they find intuitive. Now, assuming that there is a shared prior, as in the interface and the human both know that they are biased, albeit subconsciously biased, towards a certain method of interpretation, we know that the second term is true. We know that there's more, if the interface is acting according to that prior, then there's a better connection between the human's actions and the hidden information. Now, we can approximately bound that second term using the initial mutual information term and the KL divergence between our interface mapping and the prior. And the KL divergence is defined below. It's not terribly important unless you want to know the derivation. When we form this in our objective function, it's incredibly messy, as expected. But we can actually apply limit here, just like before. If we try to apply limit to the first, it succeeds. We have to modify the denominator a little bit, but that's okay. And we can also minimize the divergence from the prior using a simple MSE loss. So for an observed signal sampled from the prior, we try to minimize the distance between what the human expects for that signal to be for the hidden information and the actual signal that's provided by the interface. And we append that to our initial loss function. However, it's not actually clear what priors are user-friendly. So this took a little bit of thought. And in my opinion, it's much better to have functional priors, ways to make the interface more symmetrical, so you don't need to pull the user for feedback on what they think the interface should be. So the first prior I'll discuss is proportionality. Now, this is based on prior work that deals with the reverse direction. How can the human communicate with the robot Specifically, in this case, it was for learning user-defined mappings for robot control. And we take these signals in the hidden information and we say that their difference should be proportional. And you can force that with this loss function, which is derived from the prior work. It's a little bit different, but what this enforces is a relatively proportional structure about randomly sampled thetas and signals. Now, we can also enforce convexity in the interface. So this is a little bit technical, but we wish the state space, or for a particular hidden information packet, we wish the state space to be relatively convex, or the magnitude of the signal to be relatively convex about the state space. And I've included a proof of this in my appendix. You can actually enforce this and a global minimum at 0, or theta equals negative theta, using this loss function, which is surprising to me that it's so simple. And I have examples of what these distribution or the signal mappings look like for these priors in my appendix, if you're interested. So we used more complicated environments for these next simulations. So I ended up using a multi-layer perceptron human for these. When applicable, i.e. when we're not testing the baseline, the humans are pre-trained with knowledge of the priors. And it should be clear that the humans were not tested with these interfaces. They were simply, the prior was simply enforced upon their perceptive layer. So like before, we had an n degree of freedom environment, which we'll call it treasure environment, where the human's trying to navigate to the position of the hidden information, and they observe the reward at the end of the interaction, just like before. We tested this in 2 to 8 degrees of freedom, and in all cases, limit with a convex prior outperforms baselines dramatically. And that's a huge gap between those two. Now, we also tested with a combination of the proportional and convex prior, because you can choose any combination of prior you want. And shockingly, it actually performed closer to a proportional prior. You'd think that together these two would outperform. And it's not entirely obvious to me why that happens, but that's what the data suggests. Now, we also tried a little bit more complicated environment where the human's trying to navigate around an autonomous vehicle. And the autonomous vehicle's policy is parameterized by the hidden information. So the interface must signal the robot's policy, and the human must interpret those signals to know how the robot will respond to their actions. And the humans does observe a reward every time step, but it's based on if they've collided with the autonomous vehicle or not. And here, limit with a convex prior also vastly outperforms baselines, which is surprising as well. You'll see the collision rate drops to 0 pretty quickly. So we tested the exact same environments in in-person user studies. So the first you'll see is the treasure environment. Here, the interface is a two-dimensional signal. The human's trying to navigate to a position in the environment, and after 10 seconds, the position of the hidden information is revealed, and the user gets to know how far they are, and then the interface updates its mapping. Here, limit with convex prior outperforms other baselines. We tested Bayes, and we also tested limit in this user study. You'll see the moving average of their performance on the bottom. I'm sorry that left-hand side is a little bit hard to see. It might be the glare. But you'll see towards the end of this section that limit with convex prior outperforms subjectively and objectively. Now, for the highway environment, the signal was lower dimensional. And you'll notice that the signal updates according to the robot's policy, which is the orange vehicle. It either will be a little bit aggressive or a little bit passive, or fully aggressive, fully passive, some mix of those. So there you'll see it was swapping with the green car, which is the human's vehicle. Oh, and there's audio here. I'm sorry about that. I didn't realize. So here, limit with a convex interface is much more interpretable for the human. Eventually, Bayes does drop to 0, but it's very noisy. And you'll notice in both cases, limit, according to an ANOVA test, outperforms baselines in terms of measured error and collision rate. And subjectively, people seem to prefer limit with a convex prior, but it's not entirely clear. The only a place where we got significance was with a consistent mark in the treasure environment, but you'll see that limit on average outperforms baseline subjectively as well. Okay, so that brings us to the end, and I'll open the floor for questions. We've developed a proxy to conditional mutual information using the limit algorithm, and we do so with a combination of loss functions that are not too complicated, while we also conform to user-friendly priors on interface design using the KL divergence between the human's expected prior for signals and the interface prior. And I also have a few plots I'd like to show. Hopefully these will play. No, they won't. Okay. I can pull up those videos later if people are interested. But I have representations of the manifolds that are generated using those priors that I mentioned before, if anyone would like to see them. But that concludes my presentation on adaptive interfaces for human-robot collaboration. Cool. So now I'll open the floor up for general questions. And someone has raised their hand. You can type in chat, or you can.
He was clapping.
He's clapping. Okay. Nice. Thank you, Antonio. So I'll open the floor for questions. You can type in chat or unmute. Or people can talk here as well. Everyone knows my research already. We have no questions.
Perfect. Oh, yeah, I can. Good question. So I want to learn from your experience. You mentioned about interfaces, and and you also mentioned these neuroscientists talking about these complex things going on in the human brain, which involves past experience, our understanding of emotions. So do you think we need to go far away from modeling humans, more focus on interfaces, or we need both? What is your high-level comment?
Well, we can't, I think we still need to model humans. I don't think we can get away from that. But I think we need to recognize that. So, for example, we typically have a mathematical model of the human, like there's a Boltzmann rational model, there's XYZ model. But the research has shown in like the neurosciences, like I said, people have biases that you can impose upon those mathematical structures to enhance results, for example. So in the graph that I showed, or the plot that I showed before, and this might be, I think this should be obvious. It's obvious to me that here people expect to linearly interpolate between extremes. That's something you could impose upon a human model, but we don't currently do that with the mathematical models that we use. But there's simple things like that that rapidly accelerate adaptation, co-adaptation for that matter, that you could impose. So I think you definitely need a combination of the two. I know it's not very an abstract of an answer, but
I appreciate it. Yeah, I just want to know this is a little bit different. We not allowed the model human behaviors, what action they take, but I was wondering maybe it's in somewhere too, but I appreciate it.
Yeah. So during my user study, I was curious because people are very random, and I was wondering how well does the human model that limit generates actually fit what the human does? And in most cases, the best model for a human is a random walk. It's like I can't interpret them. There's no way I can write a model that's perfect for every human if they behave randomly.
Yeah,
so yeah. Instead, I think it might be beneficial to have a model for their interpretation. I think that might be more important than knowing their actions, because we always talk about belief, like what they believe. If we have a better model of what they believe, then we can generate, for example, in my case, signals that align with that belief. So I think there's ongoing work in that regard, at least maybe at Purdue. So it's very interesting. Yeah, what's up?
I was just gonna ask, so it looks like limit reaches a lower loss than all the other versions, but it looks like it takes about the same amount of time to reach that value. Is there any way to potentially reach that value faster than the other versions you're comparing it to?
Aside from tuning, I'm not sure how the existing loss functions could be adjusted to accelerate learning. I hope that answers your question, because I saw that as well, and it was very surprising. It's like almost the same amount of interactions that they had that jump. For example, I think you're referring to like this slide.
Yeah, and most plots, they have that same like
Yeah.
slope and then they.
And this is surprising. It's like the exact same amount of time, but it reaches a different bound, which is weird. Very weird.
Perhaps the human takes some time to co-adapt as well.
That could make sense, but it's confusing to me that the human takes the exact same amount of time to co-adapt.
Sure.
I mean, this is averaged across, I think, 10 simulations or something. And this is a moving average, of course, but that could be a possible explanation. Yeah, that's it.
Can I ask you a question about like neural networks? So you've said you've used them as a stand-in for humans. Can you talk a little bit about like how you did it, and also like, did you have any observations compared to maybe the user studies you've done? Like, is there like a, are they more similar, or you're like, well, the models are far too simplistic an approximation?
It's very tricky because they're very efficient in their computation, and they will, neural networks, not humans, will inverse.
Some humans are efficient.
Some people, not in my groups, will invert the mapping between signal and hidden information. It's like, oh, well, obviously this is the correct mapping. I've observed it over repeated interaction. So now I know what the hidden information is. So I'll take the best action. And you don't want that. So you want a simple model, but then you can't encapsulate the intricacies of human behavior. So there's a trade-off there where we use very simple neural networks to train in simulation because we didn't want them to learn the inverse mapping. Accordingly, we also made the interface mapping the neural network complicated, so the human couldn't inverse it or invert it clearly, except through training by a limit. So I don't know what the trade-off is for in-person user studies, because for the in-person user studies, we pre-trained the interfaces with a simulated human, which helped convey the hidden information more clearly.
Okay, so you think there is at least some correlation, because it certainly helped.
Yes, it definitely helps. Yeah, but most of that pre-training is for the interface, not for the human.
Right.
Yeah.
So I guess it's always easier going this way, just the human to the robot agent, whatever, or like
Yes,
backwards.
yes. The backwards direction is very difficult.
Yeah. In my experience too.
Yeah, and I still don't have a good solution for that.
I don't think anybody does. But yeah, thanks for your answer.
Yeah, of course. Does anyone have Zoom have any questions? You can type in chat. Okay. All right. Does anyone from my committee have any questions for general, or do you want to kick them out?
Yeah. I think it's probably best we can, if you guys don't mind, we ask you to leave and we can. Yeah. Okay.
All right. That goes for everyone on Zoom as well.
Food over here. You invite some food.
Okay, so everyone on Zoom, thank you for coming. But I'm gonna have to kick you all out except for Kaveh.
Yeah, don't.
Very important.
Dr. Hunt.
Yeah,
Thank you.
Thank you, Josh.
Thank you guys for coming.